So in this class we are going to mainly discuss about the dissociation of weak acid and weak base. Okay, so the objective of this class is to discuss about okay, the dissociation of weak acid and weak acids and bases. Okay, bases. So this is our aim. Okay, so first of all we are going to discuss about the weak acids, then we are going to discuss about the weak base. Okay, so first we are going to discuss about the dissociation of weak acids. Okay, weak acids. So here the terms, actually the dissociation, we have already noted ionization is different and dissociation is different. Okay, so dissociation means what? The separation of the ions. Okay, when we actually add the ionic solid in a solvent, let us suppose in a aqueous solution, okay, that is water, then because of the high dielectric constant of that water, the Coulombic interaction between the positive and negative ion will be less. Okay, intermolecular force of attraction will it will decrease actually. Okay, thus they will going to dissociate it completely into their ions. Okay, in the solution, that means they can move freely. Okay, that's why we get the conductivity of that electrolytes. But here in case of weak electrolyte, that means weak acid or weak base, actually they will not going to completely dissociate it into their ions. Okay, because they are we already noted only in the case of strong electrolytes like the salts and the strong acid like HCl or sodium chloride salt. Okay, and also let's suppose sodium hydroxide strong base. Okay, they will going to dissociate it completely. But in case of some weak acids like ammonia, acetic acid, or weak base like ammonium hydroxide, they will not going to completely dissociate it into their ions. Okay, so here we in this class we are going to discuss about how much actually the extent of dissociation, how much ions or how much that weak acid will going to dissociate into their ions. We're going to discuss about this quantitatively. Okay, so let us suppose we have a weak monobasic acid. Let's suppose HA. Monobasic means it will going to give produce one H positive ion. Okay, so this is your monobasic acid, and we add that monobasic acid in water. Okay, so when we add that monobasic acid in water, then it will going to what? They will going to first dissociate it into their ions, H positive and A negative. But here, because this H positive is this is H positive. Okay, because this H positive is the size of the H positive is very small. Okay, so what will going to happen? They will going to solvate. That means solvation occurs. Solvation means the water molecule is going to surround this H positive charge. That means H positive, this is positive, there will be some positive charge, no? And because they are in the water molecule, there will be some dipole moments. Okay, del negative and del H positive, like this one, you see, H del negative, del positive. So here H positive is there. So this H positive will going to be surrounded, or the water molecule will going to make a sphere. Okay, which will going to surround this H positive ion. Okay, and they will going to make a sphere, and this is known as actually solvation. Okay, or hydration. So it will going to make H2O positive. So we'll represent this one. So this is the forward reaction. But here, because this is a very this is a weak electrolyte, so there will be a reversible reaction. Okay, Understand? Because the dissociation process is not so fast, so that product, that means this ion can again recombine with each other, and they can form this HA and water. Okay, so we have this reaction, or this actually equation. Okay, so we can use the law of chemical equilibrium here, because this is your reversible reactions. Okay, so in case of reversible reaction, we know that we can apply the law of chemical equilibrium, and the law of chemical equilibrium is already discussed in the previous class. Okay, so I'm not going to again tell about that law of equilibrium, but we know that according to the law of equilibrium, we can write the equilibrium constant for this reaction. Let's suppose the equilibrium constant for this reaction is Kc. Okay, which is equal to what? We know that equilibrium constant can be written by using the law of chemical equilibrium by actually is equal to, we have to write here we have to multiply the concentration of the reactant, not reactant, product. Okay, product in, so it will be, your product is H2O positive, A negative. Okay, and here order will be here 1 mole and here 1 mole, so here 1 1. Okay, so if you want to write, then you can write 1 1, but here it is same. If you don't write, it's okay, because it is 1 1, so 1 is 1. Okay, but and here we have to write the reactants. So reactant is HA to the power 1 H2O to the power 1. Understand? So this is your equilibrium constant, and this is coming from the law of chemical equilibrium. Okay, so now interestingly, if you notice this this relation, then here we have what? Water. Okay, but here the solution is a very dilute solution actually. Okay, so the solution is actually very dilute. Okay, so the meaning of it is that the concentration of this water will not going to change. Okay, that means it will be the concentration of the water. We can actually take the concentration of water as a constant, because it is the amount of water is in excess amount. Okay, very large excess amount, so that's why we can use the concentration of water as a constant. Let's suppose that constant is actually is equal to, let's suppose K. Okay, is equal to, okay, so it's actually a constant. Again, before here again you see the actually this is what this actually square bracket represent the concentration. Okay, and the unit of, usually the unit of the concentration, we represent the concentration as molarity. Okay, and molarity or moles per liter, same thing. Okay, moles per liter and molarity, same thing. So we have this information. So now what we can write, we can use this relation. So here Kc is equal to what? Is equal to your H2O positive, A negative. Okay, here HA. Here what we can write? We can write the K, which is a constant. Okay, so since here you see here this Kc is also a constant, which is your equilibrium constant, and this is also a constant. So we can multiply this one, the cross multiplication. Then the cross multiplication will going to result a new constant. That means Kc into K. These two are not constant. Okay, so is equal to actually HA H2O positive, A negative. Okay, so this actually this is a new. If you multiply a constant with a new, another constant, then it will going to give again a constant, and that constant will be, let's suppose this will going to give a new constant, which is, let's suppose this is Ka. Okay, so Ka is equal to HA. Okay, so Ka is equal to actually Ka is equal to HA H3O positive, A negative. Okay, understand? So here the K is the new constant. Okay, which is actually equal to Kc into small k. Okay, so we have this relation. Okay, so this is a very important relation, so please remember this relation. Okay, we have these relations, and this is for what? The dissociation of weak acid. So Ka represent actually the dissociation of the acid, weak acid. Okay, dissociation constant of the weak acid. Okay, and actually, what is the significance of this equation? In place of H2 positive, we can write H positive. Okay, so we can write here Ka is equal to H positive, A negative, and HA. Okay, so this is the final relation. This is the final relation. So please remember this relation. Okay, very important relation. So the physical significance of this one is that the product of the concentration of H positive, that means hydrogen ion, and the anion, which is A negative, actually irrespective of their source, okay, whether they may be furnished from the acid, that means the weak acid, or maybe it will this H positive or A negative maybe come from the other substances which are present in that solution, okay, divided by the concentration of the unionized acid is equal to a constant, and that constant is actually known as dissociation constant of the weak acid. Understand? Clear? So this is the definition of the dissociation constant of a weak acid. And this actually Ka actually depends upon the temperature. Okay, so if the temperature of the system will going to increase or decrease, then the dissociation constant is going to vary. Actually, this will going to vary with temperature. Okay, it is like other equilibrium constant. In case of other equilibrium constant, that is from in the chemical equilibrium, we have some equilibrium constant, and that those equilibrium constants are also depends upon temperature. No? It is like those equilibrium constants. Okay, since we can represent this reaction or this equation by this relation or this equation, because you see here if you follow this relation, then we have this this equation of that Ka. Okay, if we follow this equation, then we have this relations or this equation. Okay, so we can use this reaction instead of this one. So we know that we can use Arrhenius equation or Arrhenius concept in this reaction. So indirectly we can adopt actually Arrhenius concept in case of weak acid. Okay, understand? Now let us calculate the relative strength of weak acid. Okay, relative strength of weak acids. Okay, so that means relative strength of weak acid means we are actually going to compare different acids, okay, different weak acids by using one relation. Okay, so actually we can relate, or we can actually express the dissociation constant, which is actually Ka. Okay, dissociation constant of a weak acid by using the degree of dissociation, where alpha represents degree of dissociation of that acid. Okay, so degree of dissociation means how much H positive ion can be obtained from that acid, weak acid. That means how much that the H positive, that the hydrogen ion can be furnished by that weak acid is calculated by the degree of dissociation. That means degree of dissociation is the actually it will going to give you the quantitative idea of the dissociation of a weak acid. Understand? So let us suppose we can actually understand the comparison of the weak acids by using some example. Okay, let's suppose we have a weak acid which is CH3COOH, acetic acid. Okay, we know that acetic acid is a weak acid. So and it will going to give you H positive and plus CH3COO negative. So here we actually add this acid, weak acid, in water. Okay, but we can actually omit water, because again in the previous topic we already discussed that we can omit the water because it is in excess amount, no? Because the concentration of the water is almost constant, so we can omit that. Okay, so we can represent this does reaction like this. Okay, no problem. So now let us suppose the initial condition, that means initial condition. At initial condition, let's suppose the concentration of that acid, that acid is, let's suppose, C moles per liter or C molar. Okay, then at initial condition, that means at t time is equal to 0, when we just when you add that acid, weak acid, in just water, okay, then they will not going to immediately dissociate into their ions. It will going to take some time. Okay, so that means at that time t is equal to 0, the concentration of H positive and the concentration of that negative ion will be 0, because no dissociation process is not going to occur at that time. Okay, so but at equilibrium position, at equilibrium condition, okay, because it will going to, this acid will going to dissociate into their ions. Okay, so let's suppose the dissociation, the degree of dissociation of this acetic acid, let's suppose it is alpha. Okay, so if degree of dissociation of this acetic acid is alpha, that means this alpha, then the concentration of that H positive ion which is formed during this process will be C alpha. Okay, similarly this one also C alpha. And here actually, if C alpha will going to form, okay, C alpha concentration of H positive ion and C alpha concentration of your negative ion that will be obtained during this process, then there will be some we get this concentration from this one now. So that means the concentration, that means at equilibrium condition, the concentration of this will going to decrease by this amount. Okay, so we have to write C, actually this is C alpha. Okay, C alpha, C minus C alpha. Okay, because C alpha is obtained from this C, so we have to write C minus C alpha. So we can take common C, so it will be 1 minus alpha. Okay, so this is the equilibrium condition. That means the concentration of acetic acid, that means that weak acid, at equilibrium condition is C1 minus alpha, and the concentration of H positive is C alpha, and the concentration of CH3 COO negative, that means that anion is C alpha. Again the thing is that we can represent this we can actually represent the Ka, that means the equilibrium constant, which is Ka, by using the law of law of chemical equilibrium. We can write this one, Ka is equal to what? Here H positive into CH3 COO negative, okay, divided by the concentration of the reactant, okay, which is CH3 COOH. Okay, simple. So now here what we can write, we can substitute this value, okay, in this relation. So we can write here, in place of H positive we can write C alpha into again C alpha, okay, and here in place of CH3 COOH we can write C into 1 minus alpha. Okay, so this C will going to cancel this one. Okay, then eventually it will become what? It will become your actually C alpha square 1 minus alpha. Okay, so this is your Ka. Again, since we we already considered that the solution of this weak acid is very dilute. Why dilute? Because they will going to dissociate it. Actually the dissociation is very less, na? So it will be very dilute solution. The strength of the solution is very dilute because of the very weak dissociation of that electrolyte. Okay, so if the dissociation process, that means degree of dissociation, is very small, that means what? Alpha is very small. Alpha is very small than 1, because the degree of dissociation, because we can write that because the dissociation process is what? Dissociation process is process is very weak, very weak. Okay, degree of dissociation will be very weak. That's why alpha is very less than 1. So what we can write here, that means 1 minus alpha is almost equal to 1. So that means Ka is equal to C alpha square. Okay, so we have this relation now. So by using this relation we can compare the dissociation constant for different acid. Okay, different weak acids. So let's suppose we have two different weak acids. Let's suppose it's H1A1 and H2A2. Okay, so let's suppose the dissociation constant of this one is alpha 1 and this one is degree of dissociation. Okay, and the dissociation constant of this one is, let's suppose, Ka1 and this one is Ka2. Okay, so and suppose the concentration for these two is same, which is C. Okay, C concentration for both of this one. Okay, so that means we can write for these two, alpha 1 is by alpha 2 is equal to root over Ka1 by Ka2. Do you understand this one? See how we get this one? Actually we here you see, we for this, let's suppose this one, this reaction for this this electrolyte or this weak acid, the Ka1 is equal to actually C alpha 1 square, and for this one actually what, Ka2 is equal to C alpha 2 square, because we already considered that the concentration for both the electrolytes or both the weak acids are same. So in place of here C, here we can write C is equal to Ka divided by A2 divided by alpha 2 square. Okay, so in place of C, what we can write, this part can be written here, no? So we can write here Ka2 by alpha 2 square, here alpha 1 square. Okay, here Ka and 1. Understand? So from this one, if we use general mathematics, just cross multiplication, then you can get this one from this one. Okay, understand? So we can get this important relation. So that means we can relate or we can compare two different weak acids if we know the degree of dissociation. Okay, so or we can know the what is this? This is your dissociation constant. If you know the dissociation constant of that weak acid or this weak acid, then we can and the degree of dissociation of one weak acid, then we can calculate the degree of dissociation of the other. So we have this relation. Okay, so but here the thing is that this alpha, okay, what is alpha? Actually alpha represent what? Alpha is actually your degree of dissociation. Okay, so actually the degree of dissociation for that weak acid, let's suppose this is alpha 1, so alpha 1 represent the degree of dissociation of this acid, this weak acid. Okay, so this actually indicate what? This indicate, or this is actually the measure of the capacity of this acid, okay, to furnish H positive ion. Okay, hence actually alpha 1 represent the strength of this acid. Understand? So in place of this alpha 1, what we can write? We can write that the strength of one acid was, okay, divided by strength of another acid. Okay, so in place of alpha we can write strength of one acid, which is actually H1A1, and in place of alpha 2 we can write the strength of another acid. Okay, so it will be equal to root over Ka1 by Ka2. Okay, so we can compare the strength of one acid if we know the strength of other acid, and if we know the equilibrium constant of both of the acid. Okay, so we can compare this one. So by using this relation, okay, so by using this relation we can compare, or we can we can know the relative strength of weak acids. Again, we can calculate the concentration of H positive, that means this one, okay, the concentration of H positive from this reaction. Okay, so the reaction is actually CH3 COOH H positive plus CH3 COO negative. Okay, so at equilibrium we know that at equilibrium the concentration at that is the equilibrium concentration is actually what? This is actually C is equal to C1 minus alpha C alpha, and this is C alpha, no? So actually the meaning of this is that the concentration of H is equal to C alpha. Okay, and from the previous study, that means we already know that Ka is equal to what? C alpha square. Okay, so that means alpha is equal to what? Alpha is equal to root over Ka by C. So we can put this value here. So that means H positive is equal to C into alpha, that means root over Ka by C. So it will be your C Ka. So we can calculate the concentration of the acid by using the concentration, actually concentration of the H positive. That means what? The the concentration of H positive which is present in that solution. Understand? That means the number of ions, how many moles of ions are present in 1 liter of the solution, we can calculate. Okay, by using the concentration of the weak acid, that is acetic acid, and the dissociation constant of the acid. So now let us discuss about the dissociation of weak acid. Dissociation of weak base. Okay, weak, not acid, weak base. Weak base. Okay, so let us suppose we have a mono acid basic which is BOH, and we can use the Arrhenius concept to represent this reaction. Okay, so that base will going to produce one B positive and OH negative ion. Okay, so again we can represent actually, so we can represent, or we can actually calculate the value of the equilibrium constant. So let's suppose the equilibrium constant is represented by capital KB, where B is the B, we use B because of this is base, no? In the previous case we used small a, no? Because that was your weak acid. So here we use B. Okay, so this KB actually the equilibrium constant of this weak base. Okay, and this is equal to what? This is equal to actually the multiplication of B positive into OH negative, and here BOH. Okay, understand? So this is actually coming from where? This is actually coming from your law of chemical equilibrium. Okay, chemical equilibrium. Okay, this is the law of chemical equilibrium. So now let's suppose at the original concentration, or the initial concentration, or we can write original concentration, that means at time t is equal to 0. Let's suppose the concentration of the weak base is again small c. Okay, small c moles per liter or molar. Okay, so at initial concentration we know that the concentration of the B positive ion and OH negative ion will be 0, because it will not going to dissociate at t is equal to 0 time. Okay, understand? And let's suppose the equilibrium concentration, that means at equilibrium the concentration of let's suppose BOH is equal to actually we can calculate, let's suppose the degree of dissociation is alpha. Okay, so the concentration of B positive will be C alpha, and the concentration of OH negative will be C alpha again. Okay, so that means the remaining the concentration of BOH will be what? C minus C alpha. That means same thing. Okay, so we can put this value here. Okay, so if we put this value here, then the concentration of B positive is equal to C alpha. So we can write here C alpha into again here OH negative concentration is equal to C alpha. Okay, here again concentration of BOH is equal to 1 minus alpha into C. So it will going to eventually give you C alpha square. Okay, because 1 minus alpha is almost equal to alpha, because the degree of dissociation, that means the alpha is very very small, because this is a weak electrolyte. Understand? So this is your KB. So here alpha, we can write alpha is equal to what? Kb by C. Okay, so that means we can calculate the value of that OH negative, that means the concentration of OH negative, that means the number of moles of the negative ion, the OH negative ion present in 1 liter solution will be your what? C alpha. Okay, so in place of alpha, what we can write? Kb by C. So we can write this one actually C square Kb by C. Okay, so it will be your root over C Kb. So this is the concentration of OH negative. So we able to get the, or we can calculate the concentration of the OH negative ion if we know the concentration of the weak base and the dissociation constant of the weak base. Understand? And in the previous case, in case of the weak acid, we have H positive concentration, which is actually equal to CKa. Okay, so we have this information. Okay, these two information. Okay, so again we can we can actually again compare the different weak bases by using this the value of alpha. If one is alpha 1, other one is alpha 2, it is actually we can use the similar approach which is used in the previous case. Okay, that means weak acid, we can use that similar approach to calculate, to compare different weak bases. Understand? So this is all about the dissociation of weak acids and weak bases. So in the next class we are going to discuss about the dissociation of water. Okay.